Hi, welcome to EC&M Tech Talks. Today we're going to talk about motor controls in the National Electrical Code, the NEC, right? Specifically, we're going to talk about what we probably most commonly run into out in the field, and that's these control circuits that are not power limited in any way. For the 2026 NEC, we have a new article for that situation, and it's Article 206, non-power limited remote control and signaling circuits then. Wow, okay. So we're going to figure out what all of that means. We're going to talk about the individual components. We'll jump into probably a schematic ladder diagram, see how it all operates, and see how we size those conductors and make sure that we install this control circuit properly. Now, we have to remember that there are two separate circuits when it comes to motors and controls. We have the main power circuit, and then we have the control circuit. So let's start by taking a look at this main power circuit and see how the control circuit ties into that, and why the control circuit actually appears in a separate article than Article, say, 430 on motors, or whatever specific article it is, that air conditioning and refrigeration equipment, motors, compressors, whatever it is that we're working on, okay? So let's take a look at the main components then on the first circuit, and this is our main power circuit. So for the main power circuit, I start up here and I have to have some type of disconnect, don't I? I've got a requirement in Article 430 about having a disconnect within sight of, meaning within 50 feet and visible from the motor that I'm controlling then. Most often, or I should say quite often anyway, all of this stuff we're talking about, this motor, the fuse disconnect and the motor starter that we're going to talk about down here, may be inside of one control cabinet, may be inside quite often in industrial, commercial facilities, inside of a motor control center bucket, motor control center cubicle, in other words, righty? And then, of course, we have our motor down here. The motor's going to be wherever it is out in the plant. Some things that I want to have associated with controlling and operating this motor then is some type of remote control and signaling circuit, right? So I want to be able to push a start push button somewhere else out in the plant and cause this motor to operate. So I have some type of disconnect switch, and I'm going to have some fuses in here. Now the fuses are for short circuit and ground fault protection, aren't they? I can take a look at that, and that's defined in Article 240 for me, 240.4 is it? Okay, that talks about my overcurrent protection, short circuit, and ground faults. Fuses and circuit breakers are in place in order to protect the wiring, the conductors going down to my equipment. For protection of the motor itself, I have overloads that are going to do that. So let's take a look at the next part of the circuit. Let's take a look at this relay is what it is. So this particular relay, it's a special purpose relay, isn't it? Designed to start and operate a motor. So we would call this special purpose relay a contactor. And these particular contacts are designed to start and operate whatever size motor it is that I'm going to run. NEMA, National Electrical Manufacturers Association, takes a lot of the guesswork out of this circuit for me. They go ahead and they tell me up here on the label, if I take a look at it, it says it's a NEMA size 1 motor starting contactor. So a NEMA size 1 starting contactor. And the NEMA size 1, I can look it up, or it tells me right on the faceplate as well. It says for a 208 230 volt AC motor, it's rated for 7.5 horsepower. For a 460 volt or 570 volt AC circuit, it's rated for 10 horsepower. So realistically then, if I'm running, say, a 10 horsepower motor, I'm probably running 30 amp fuses up here. I've got 10 or 12 AWG wire coming down to the top of my motor starter, and those same size AWG conductors going on down to my motor. So I said just a minute ago that the fuses are designed to protect all of this wiring downstream. And that's true. What protects the motor? The overloads on the motor. So on the bottom of the motor starter, I have these overloads, one for each phase. When I take and I combine the motor overloads with the starting contactor, the whole unit is called a motor starter. So this is a motor starter, a NEMA size 1 motor starter. Now, if you're using IEC equipment, it's not sized per NEMA data, is it? So you have to look on the IEC starter and see what probably the KW and the amperage and voltage ratings are for that particular IEC starter then. So that's my main power circuit. The power comes in from wherever, goes through the fuses for short circuit and ground fault protection, through my starting contactor. When I close the contacts go closed, power supplied through the overloads down to the motor. The overloads are sized based on the nameplate data of the motor. To size the conductors, I go to tables in Article 430. Given the certain voltage, phase, and horsepower of the motor, that's how I size my conductors. Then, of course, I have to make my adjustment and correction factors and count for voltage drop if need be and all of those type things. Now, let's talk a little bit about the control of this particular relay. I can manually operate this, and this is not a good thing to do. This is not safe. But maybe you've seen people do this out in the field. I can bump the motor starter, a term you might hear. I can take my screwdriver and push on a little bar on the side of this, and maybe you can hear that, but I'm opening and closing the contacts. Not a good thing to do for two reasons. One is when I do that, I'm standing right in front of it. So if something does go wrong, it's right there in front of me. The other issue is, and one of the big issues, is that I have overridden every control element within this circuit when I do that. Any safety interlocks that I have, if the motor was not ready to start, not ready to turn, if I had a light curtain that had triggered a shutdown of the motor or whatever, it doesn't matter. That motor's going to start, and somebody could get in trouble on the other end. So, it's not, we don't go out and bump motor starters, okay? Not a good, safe thing to do. Well, if I don't want to stand here and manually, certainly, have to operate these contacts to start the motor, I'm going to do it remotely, So, as I mentioned, I'm going to take something like a push button, push my push button, and energize a coil of wire. And when I energize that coil of wire, the electromagnetic field around that coil will pull this little lever on the inside and close those contacts. And so I need to energize and maintain that coil energized as long as I want to keep the motor running. I need to keep the contacts closed, obviously. Well, in order to do that, in order to supply that coil of wire, I'm going to use my control circuit, not the main power circuit. Two separate circuits. We brought power from the fuses on down through the motor starter, down into the motor runs, that's fine, but how do I control it? That's an entirely separate circuit. This could be a 460 volt three-phase motor. My control circuit could be 24 volts AC or DC, 120 volts AC, 125 volts DC, whatever it is. Quite often what we're going to find out in the field is what? 120 volts AC. So when I buy my motor starter, I can specify what type of coil, what voltage rating coil I want in there. Let's take a look at that coil on the inside and see how easy it is to change out. I've loosened these two screws on the front on the nameplate. I pull off the nameplate. There's my coil. So I'll go ahead and pull out the coil and show it to you. I'll pull it out kind of carefully because it has some moving pieces associated with it. Alrighty. And so there we have the coil and we have the remaining part of the contactor. The contacts are back on the inside, and of course you can't see those right now. There's a little screw, screws on each corner up here, and there's a little note that tells me that I can loosen the screws in the corner, it says, in order to pull off the next section and actually access the contacts on the inside. So I can clean these contacts on a NEMA starter. I can replace them if need be, and so on, inspect them. Certainly I'll do measurements on them, all part of my periodic maintenance program. My measurements I'm talking about, I'm probably checking voltage across the contacts, or more likely, what am I doing? I'm doing low resistance ohm meter across those contacts to make sure that I, within specification on those, that they're not getting dirty. Now, if it's an IEC contactor, I can't pull that one apart. I just replace it. Let's take a look at the coil. So this is my coil of wire, and I've got some ratings on that coil, and it says it's rated for 120 volts, 60 hertz, 110 volts, 50 hertz, okay? But it doesn't give me a current rating. There is a number over here that I can go look up that number for the manufacturer, and no problem, I got it very easily. It's 2 amps. So when this coil is energized, it draws 2 amps of current flow. Great. So for my motor, I don't know, what am I drawing on a 10-horse motor? The code book tells me it's 14 amps. I don't care what the nameplate says. The code book, when I size these conductors, that's a 14 amp motor, 10 horsepower, 460 volts, 3-phase. The coil only draws 2 amps. So I probably don't need those same 10 AWG or 12, whatever it is. I'm using conductors down to the motor in order to supply this coil. In fact, I don't want to do that at all. I'm going to want to work with much smaller conductors. So that's going to be my control circuit. So how do I size those conductors that go to the coil? Well, I have to look in the NEC, right? And where am I going to look? Well, it depends. What is the power supply to my control circuit? What's going to go through all my push buttons and stop buttons and selector switches and limit switches and sensors out there and float switches, whatever I got out there in the field? What voltage is going to be applied to those and force current flow through those to this coil of wire to energize that coil and cause these contacts to go close. Now, when that coil is energized, it pulls up on this little lever and closes the contacts. So, by the way, do that, okay? Take one of these apart sometime in the shop when you got a few minutes or whatever, and take a look at the contacts, inspect it, make sure you understand how it works. If you understand how it works on the workbench, as I always say, it's a lot easier to troubleshoot something out in the field, isn't it? So anyway, I can get different rated coils. This is a 120 volt coil for 60 hertz. I can certainly buy 24 volt coils. I can buy coils for DC. I can buy 480 volt coils even if I wanted to do that. Let's take a look at how we are going to go the Article 206 in the NEC, because that's most likely what we're going to deal with, and how we're going to determine what size conductors we need based on what the power supply is to this control circuit and all of those types of things. And no, I don't need number 10 or 12 wire going to this coil. Let's take a look in Article 206 then, go through a schematic diagram, walk through it, and see how Article 206 applies. So let's begin by taking a look at our main power circuit that we've been talking about. So the power comes in on L1, L2, and L3, goes through that fuse disconnect switch, and from there it goes to the motor starter. So these M1 contacts, those are the contacts that are physically located inside the starter that we took a look at. The coil is in the control circuit. We don't see that coil on the main power circuit, do we? We said at the bottom of the starter contacts, we had the overloads. So down below is our thermal overloads in this particular unit. And if any one of those thermal overloads would open up, it will automatically de-energize the coil and stop our motor. And then of course down here is the motor itself, T1, T2, and T3, and that is our motor load. Next thing let's do is let's look at the control circuit. Entirely different circuit. This is one circuit. Let's move to the next circuit. This is my control circuit. I have a control power transformer up here. The control power transformer has a primary of 480 volts, secondary voltage 120 volts. It's protected on the primary side by fuses. Now, the rules that we're going to find for this control power transformer are in Article 430, Part 6. 430, Part 6 talks about motor controls. So that's an important part to go look at. Certainly, Article 430 then on motors and motor controllers. And take a look at Part 6. And what it's going to tell us then, it's going to give us the specific rules for what size fuses or overcurrent protection we need on the primary side of the transformer. It's also going to tell us things like, for instance, it says that if this control power transformer is located inside of the same enclosure as that fuse disconnect we just saw, say for example inside of an MCC cubicle or MCC bucket, then the control power transformer must tap off of the load side of that disconnect, short circuit, ground fault protection, in other words, the fuses that are inside of that enclosure, so that when I throw that disconnect switch to turn off power to the motor, I'm also de-energizing my control circuit at the same time. Article 430 tells me that if those disconnects are separate devices, which they're allowed to be if that transformer is not located inside the same enclosure, then they must be adjacent to each other, and gives some wording on all of that, some terminology you would need to take a look at. So anyway, let's move through down to this control power transformer. Now, one thing we said is that Article 206 is what we're talking about up here. I'll put it back up here in the corner. But Article 206 is on non-power limited remote control and signaling circuits. So how do I know when I look at this control circuit, how do I know if it's power limited or not? Well, if it's power limited, the articles for the control circuit and the wiring and so forth are going to appear in Chapter 7. In Chapter 7, I'm going to find, in fact, it mentions this in Article 206. It says for Class 1 circuits, go to Article 724, and for Class 2 and 3 circuits, go to Article 725. So if I were to go look at Article 724, that might be the first thing I would ask was, well, maybe this is a Class 1 power limited circuit. And but I look and I find out for it to be a Class 1 circuit, it can't be any greater than 30 volts. So right away, that's out the window, isn't it? Because the secondary side is 120 volts, greater than 30 volts. So I know it's not a Class 1 circuit. If it's a Class 2 or Class 3 circuit, then it is definitely power limited, but it's got to be marked up here. It's got to tell me it's a Class 2 or a Class 3 circuit. So I would need to know that. It's got to be listed as a Class 2 or Class 3 circuit, and it's got to be marked as such. So typically, we have a control power transformer. It's not Class 1, Class 2, or Class 3, and so we end up in non-power limited circuit Article 206. So we have our control power transformer, and we tap off the secondary side and get our 120 volts. Now, I come off the secondary side. One side is grounded, you'll notice. X2 side is grounded. And so that's probably going to be, yep, white wire I'm going to take off of that side, isn't it? And so I've got a fuse on the ungrounded side. That's not the size of the fuse, just the fuse number. But this fuse, let's figure out what type of overcurrent protection and what size wiring do I need down here. Okay, we're going to figure that out. That's going to be in Article 206. Let's take a look at how this circuit works. Power comes in from the control power transformer through X1, goes on down, goes through the normally closed stop push button. When I hit the start push button and close the start push button contact, that allows power to flow to where? The A1 and A2 terminals on the coil in my motor starter, not the motor, but to the coil. As I come out of the coil, of course, I get to my overload contacts. If any one of those three thermal overloads reaches its temperature to melt and the solder melts on the inside, it would trip these contacts that would then de-energize my motor coil and, of course, de-energize the motor for me. So that's how the circuit operates. Once I push the start push button up here in line 107, you can see I've got another set of contacts that go close. Those are my maintaining contacts. So I can go ahead and release the start push button. And when I release the start push button, the motor would continue to run as current would flow around the start push button and to the M1 coil, the starter coil then. One thing that Article 430 tells me is I've got to be careful. I never want to take this coil for the motor starter and somehow wire it in over here before that stop push button. That could be very dangerous. If I had a ground fault in the system, I could go ahead and energize that motor coil and bypass all of this circuitry, the start and the stop push button. So in other words, a ground fault could inadvertently cause my motor to start. Obviously, that's very dangerous. Now, let's talk about how we're going to size these conductors and this overcurrent protection for this control circuit. We're going to go to Article 206. And what Article 206 is going to tell me, it's 206.4a, size and use, all righty? So 206.4, installation, non-power limited, remote control and signaling circuits, it says, shall be installed in accordance with 300.4 to 300.25. Oh, so all of those other rules back in Chapter 3 still apply. Yeah. Okay. What about my raceways and all of that I'm going to put this in? Yeah. That's all found in Chapter 3. So that information still applies from Chapter 3, except for the sizing of these conductors, we can do something different. By the way, while I'm talking about it, as far as the raceways, can I put the wiring for this control circuit inside the same raceway conduit as I can that main power circuit? And the answer is yes. It's found in Article 206. And it tells me that I can, as long as I meet the insulation requirements on the conductors. And by the way, the insulation requirements, it tells me that for this control wiring has to be at least no less than 600 volts. So I shouldn't have any trouble with that, right? And also they're functionally associated, obviously, the control circuit, the main power circuit for the motor. So yeah, I end up being able to put them inside the same raceway. But let's get back to sizing these conductors. 206.4a says installation and maximum load. What it's going to tell me is, rather than go to 310.15 and say, hey, well, you calculate your load and blah, 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 and you go to this table in 310.16, right? Table 310.16. It says, no, I can go to Article 402 to size my conductors. And what's Article 402? It's fixture wires. So I can size these conductors based on fixture wires. And it references the table in Article 402. And it's pretty simple to read. Once you look at it, it says for 18 AWG copper, I can go ahead, if the load is no more than 6 amps, I can use 18 AWG copper. If it's no more than 8 amps, my control circuit load, then I can use number 16 wire. Well, we already looked up the manufacturer's information, didn't we? And we said that coil would draw 2 amps of current flow. Now, there were some LEDs actually in those push buttons that we took a look at, but that's going to be a pretty low value as well. So if we go through and we calculate up in this particular circuit, we're certainly going to be a lot less than 6 amps of current flow. So we could go ahead, according to the table in 402 on fixture wires, we could use 18 AWG right here. Okay, so we could use 18 AWG. Red probably is what we're going to use, not required by code, but I'm probably going to use red over here on my ungrounded conductor size. And then I'm going to use white 18 AWG over here for my grounded conductor side. So that's great. I've been able to use a heck of a lot smaller wire. I've saved the boss some money. It's going to be a lot easier to work with, number 18 wire and so on. And now the next thing I got to be concerned with is, what about my overcurrent protection? Well, that's easy. I go to 240.4D, and 240.4D says that on number 18 wire, I cannot go any larger than 7 amps. So I could put a 7 amp fuse in there. But wait, okay, and I'm probably not, but I might go with something smaller. But I could put a 7 amp fuse on number 18 wire. But according to the table in 402, number 18 wire had an ampacity of 6 amps. So I'm allowed, because of the inrush current drawn by that coil when I energize it, I'm allowed to use that 7 amp fuse on that number 18 wire. So that's how I size my conductors and my overcurrent protection for this control circuit. And remember, I've also got to go look in Article 430, specifically Part 6 on motors, for information on my control power transformer up here and installation requirements for that. So you want to make sure and take a look at 430. Then you could get into other equipment as well, couldn't you? Suppose this motor were actually an electric motor driving a fire pump. Oh, that's pretty important. Do I really want overloads on my fire pump motor? I don't think so. So those would probably go away if I take a look in Chapter 6 for specific equipment and look at that fire pump. Because really, if I got a fire going on, do I care if the motor is overloaded? Keep pumping water, man. The building's burning down, all right? So that's pretty important. So anyway, so whether I'm working on overhead cranes or elevators or whatever it is, go to Chapter 6 on your specific equipment and look up those specific details that you need to. But so far, we've looked at Article 206 then on the non-power limited remote control and signaling circuits. Remote control, I push the push button and the motor starts far away from me, right? That's remote control. And signaling, when I push the push button, a light comes on and lets me know that the motor's running. So anyway, remote control and signaling circuits. Probably going to be a lot of non-power limited work that you do, but hey, I'm not saying you're not doing class 1 and 2 and 3 circuits certainly out there as well. So take a look at that information in Chapter 7. Alrighty? So that is the basics of Article 206, or pretty much in detail on Article 206, and motor control circuits. So that wraps it up for NEC Article 206, non-power limited remote control and signaling circuits. The main thing is that when you go in out there and to work on all of this crazy wiring involved in these control circuits, is that you'll work safely, and we'll see you at the next Tech Talk.